The Talon V you're asking about traces its lineage to the original Talon family developed by Foster Miller in the United States and now produced under Kinetic North America after Foster Miller was acquired. The platform's evolution has been a collaboration between field operators, feedback EAD teams, special operations, first responders and incremental engineering improvements at Foster Miller Kinetic to make the vehicle more modular, rugged, and interoperable with third-party systems. The robot's invention was iterative rather than a single, aha, moment. The original Talon designs appeared in the late 1990s and field deployments began around 2000, with wide operational use through the 2000s in Iraq, Afghanistan, humanitarian responses including Ground Zero in 2001 and later formalized generational upgrades that produced the Talon V, also styled Talon 5 Talon V. The Talon versus itself was publicly introduced as the next generation, man-transportable tactical Talon at events such as OSA in the mid-2010s as Kinetic consolidated the platform and added interoperability and modern electronics. At its core, the Talon V's main features and specifications emphasize tactical mobility, modularity, and mission configurability. It is a rugged tracked unmanned ground vehicle designed for EOD, reconnaissance, CBRN, hazmat, and other tactical tasks. It supports multiple camera payloads including HD day cameras and thermal night sensors, offers a dexterous manipulator arm on EOD variants, has an optional high-performance drive motor able to achieve speeds up to roughly 6 miles per hour and climb steep inclines or a 45 degrees staircase in certain configurations, and furnishes a broad set of I/O ports and communications options including MPU-5 radios and fiber or RF links. The Talon Versus was built to be IOP JAWS AS4 compliant, so it can plug in third-party sensors and devices and supports autonomy and mapping features where needed. Dimensions and configuration options vary by variant: recon, EOD, hazmat, but the datasheets list compact, man-transportable footprints roughly in the tens of inches for height with length in standard configs and multiple power options including lead-acid and lithium-ion batteries for different endurance trade-offs. Physically, the Talon family uses a tracked chassis with a low-profile design engineered for harsh environments. Construction emphasizes durable, field-serviceable materials and components, reinforced aluminum and composite housings for electronics bays, stainless or treated steel for key mechanical linkages, and sealed enclosures to resist dust, moisture and chemical decontamination procedures required for hazmat work. The manipulator and structural components are optimized for payload versus weight. Lightweight arms for reconnaissance variants and higher torque, stronger arms for EOD engineer variants that must lift tens of kilograms and exert significant gripping force. The overall package is balanced to be man-transportable, packable into a vehicle or carried by a technician while still robust enough for repeated field use. Exact alloy and composite formulations are typically supplier details, but the product literature emphasizes ruggedized metal frames plus sealed composite electronics housings for survivability and ease of maintenance. Mechanically and electronically, Talons operate as remotely piloted platforms with optional autonomy layers. The basic working mechanism is a tracked drive train powered by electric motors, a motor controller and battery subsystem, and a manipulator arm driven by electric actuators, servo or brushless motor actuators with gearbox reductions that give multiple degrees of freedom for fine manipulation. The sensor suite typically includes multiple video cameras, color zoom, wide-angle, low-light thermal imagers, microphones, and on hazmat variants chemical CBRN sensors or radiation detectors. These sensor streams are transmitted back to the Operator Control Unit OCU via encrypted radio or fiber links. Higher-level software provides mapping, waypoint navigation, and limited autonomy, obstacle avoidance, path following, and the Talon Versus platform is built with an open architecture and JAWS IOP standards so integrators can add autonomy modules, SLAM mapping stacks, or third-party perception systems. Actuation for driving, steering and manipulation is handled through closed-loop controllers, encoders, torque feedback, while situational awareness is provided by multimodal sensors. The operator fuses video, thermal and telemetry to make decisions, though the platform increasingly supports autonomy and mapping features to reduce operator workload. Price and cost are more variable than the spec sheet because Talons are sold in many configurations and to governments or approved agencies. Historically, public reporting for Talon variants shows a wide range. Earlier public figures and secondary sources have listed figures from the low hundreds of thousands for tactical variants to several $100,000 for weaponized or heavily instrumented systems, and older public references which mix variants and packages sometimes cite larger program costs for fleets. Estimates commonly referenced in open reporting place single tactical Talon variants in the ballpark of roughly $100,000–$300,000 depending on armament. sensors and warranties, while specialized builds, swords, weapon integration experiments, deep CBRN kits, or full logistics support packages push that number higher. Program procurement and fleet-level contracts including spares, training, and logistic support can increase life cycle costs substantially. Because Kinetic sells to government and authorized agencies and pricing varies with options, configuration and buyer, any procurement should be quoted directly from Kinetic or an authorized distributor for an accurate current price. The country of origin for the Talon design is the United States. Foster Miller, an American company, conceived and produced the original Talon robots, and after acquisition the product line continued under Kinetic North America. Kinetic is a UK firm with a North American subsidiary that manages production and support in the US. So while Kinetic is an international defense company, the Talon family's engineering and fielding history is rooted in U.S. R&D and procurement. Looking to future benefits and applications for humanity, Talon-class robots demonstrate several clear societal advantages. They remove humans from the highest-risk tasks: bomb disposal, hazardous material reconnaissance, post-disaster search can be rapidly retasked for disaster response, structural inspection, collapsed building access, and serve as modular platforms for scientific sensing in contaminated or unreachable environments. As autonomy and perception improve, Talon-style vehicles could autonomously map dangerous zones, perform repetitive sampling, and extend the reach of first responders, lowering casualties, shortening response times, and enabling safer handling of chemical, biological or radiological threats. In low-intensity settings, smaller, cheaper variants could be used for critical infrastructure inspection, environmental monitoring, and remote industrial maintenance. There are also a number of less-known or hidden facts worth calling out. Talon units were used in high-profile non-combat operations such as the Ground Zero recovery effort after 9/11, where they demonstrated long-term survivability in contaminated environments. The platform spawned several specialized offshoots: Hazmat Talon, Sodalon reconnaissance variants, and even experimental swords weapon mounts, which illustrate how modular chassis designs can be repurposed for different missions. And because Talon has been fielded in large numbers, much of its maturation has come from iterative feedback from EOD teams and actual combat hazard experience rather than purely lab testing. That operational feedback loop is why the arm's strength, survivability, and controller ergonomics evolved as they did. Also, public price figures are often conflated with program or fleet contract totals, so simple, per unit, numbers in open sources should be treated cautiously. Finally, possible future developments and impacts. Expect the Talon family and similar tactical UGVs to trend toward more integrated autonomy, improved SLAM, cooperative multi-robot mapping, and shared autonomy where the machine handles low-level driving and the human handles high-level decisions, lighter and longer endurance power systems, improved lithium-ion chemistries or hybrid power modules, tighter sensor fusion, RGB, thermal, lidar and acoustic analytics, and more standardized open interfaces so plug-and-play payloads become routine. On the policy and societal side, these robots will continue to raise questions about weaponization, export controls, and rules of engagement. Lessons from the swords experiments slowed weaponization efforts, showing that deployment choices have ethical, legal and political dimensions. If managed responsibly, the technological trajectory points to safer explosive ordnance clearance, faster disaster response, and wider civilian benefits: infrastructure inspection, environmental sensing. If managed poorly, the same capabilities could complicate arms control or raise domestic law enforcement concerns, so transparency, standards and export controls will matter as much as the hardware improvements.